All right, so picking up on chapter 7, we're going to talk about dispersion in colors. So when we talked about our luminescent or incandescent light sources, it's important to be specific that these are going to be white light sources, meaning they contain all of the colors. Now, we know that if an object absorbs the light and only reflects out one color, that's how we see red or orange or yellow specifically. But we can also separate the colors with a prism. A raindrop is going to act very similar to a prism. And so what will happen is the white light comes in, hits the surface of the drop. It's going to have its first refraction, so it's going to bend. Then it's going to reflect, and then it's going to have its second refraction. And so then eventually what we'll see in the sky is a nice, maybe not an entire rainbow, but we end up seeing the red, the orange, the yellow, the green, the blue, the purple, the violet. And that's because each raindrop is going to act as an individual prism, separating the light. Now, dispersion is what's happening here. It's just taking the white light and dispersing it into individual colors. And that's because the index of refraction, meaning how much it bends, is going to vary with each wavelength, which really we can think of as each color. So each color is going to have a unique wavelength, and therefore it's going to bend differently. So different wavelengths are going to refract at different angles. This right here. That's our angle. Therefore, we're going to get unique colors. So violet color is going to refract the most, which gives us our blue skies. And red is going to refract the least, which is what gives us red sunsets. Because if you think about the Earth going around, so this is the Earth. Doesn't look like the Earth, but that's okay. And at night, the sun is going to go down. Now, what happens as the sun goes down is that the light around the Earth is going to start being dispersed. And so what we'll see is what's left of the light that gets bent the least, which is the red, which is why when the sun goes down, we tend to see red, orange, yellows, but we don't always see the green, blues, indigos, and violets. Okay, we'll see those first couple of colors. And then another example, of course, is the formation of a rainbow. So optics are the use of lens to form images. Okay, we're going to have two different types of lenses. We're going to have a concave and a convex lens, kind of similar to the same idea of the mirrors, except for the lens is going to behave in a way that's different than the mirror, because the mirror is going to reflect back, but the lens are going to basically absorb and then transmit the light coming in. So we're going to have two different kinds. We have a concave, which is a diverging lens, and then convex, which is a converging lens. And the difference here is when the light of the concave is coming in, so you can remember it's concave, it's caved in. As it's coming in, it's going to hit this surface and then it's going to bend out. And only the one that hits exactly in the center is going to pass through. Okay, so it's called diverging because the lines here are moving away from each other. Okay, most of the time this is used in vision correction in association with other lenses. Now convex lenses are going to be converging because as the light comes in and hits the surface, it's actually going to bend in. And what happens is there's going to be a single point where all of the lines are going to pass each other at the exact same time. Now these are the most commonly used lens in like your magnifying glasses, your cameras, your eyeglasses, and telescopes. So vision correction is going to be this type of lens. Okay, if you're using a concave lens, you're also using something else in conjunction with that, not in itself alone. Because if you think about it, we're going to see on the previous slide, this is where the image needs to be transmitted to your brain. Over here, there's no single focal point that will allow the image to be formed and then transmitted. So let's talk about the human eye. There's a couple of important things here. We have what's called a lens inside your eye. It's convex because it's going to point out. So what that means is we're going to have a single area where the lines are going to cross, and we need that to be on the back of the retina because there is an important nerve that goes from the back of the retina to the brain, which then processes the image. So when you have normal vision and you're viewing something far away or something near, all of the lines are going to cross right there on the back of the retina. Therefore, it's going to pass that image along quite well. It won't be blurry. It'll be very clear, and it'll be just fine. When you need correction of your vision, it's because you're either nearsighted or farsighted. If you're nearsighted, what will happen is the image forms too far into the eye. So this distance right here, it's too far away from your optical nerve for it to be transmitted to your brain, so you can't see very well. But when you have eyeglasses for correction, what that does is it causes the image to form a little further back on your retina, which allows for the image to be transmitted. When you're farsighted, it's the opposite problem. The image is forming too far back behind where it needs to be forming. Therefore, when this image is received right here, these pink lines have not even crossed yet. So you're going to have blurry vision and be unable to see for that reason. And so then you would have glasses to do the opposite. Your glasses would be moving the image further up, forward, so that you could process the image correctly on the back of your retina. So properties of light. Having said all of that, there are two different explanations about how light behaves. The first one is the light ray model, and the second one is the wave model. And for a long time, there were kind of people in one camp or the other camp. They did not agree that it was one or the other. There's a lot of disagreement, and we're going to talk about what we understand now. So the light ray model treats light like it's a particle, and we're going to call those particles photons. So they're particles just like electrons, just like neutrons, just like protons that we talked about in electricity. The only difference is they're photons, they're particles of light, not particles that are negatively charged or positively charged. And we're going to say here that they travel in straight lines. Now the applications of these are the things we talked about: mirrors, prisms, and lenses. Those are all things we really understand quite well, that when an electron interacts with matter, it can be absorbed, it can be reflected. And so if a photon behaves similarly, it's easy to imagine that they're probably closely related to each other. However, the wave model is going to take into account some things that the light ray model does not. And what the wave model says is that light is a wave, just like sound. So it's not made up of particles, it's just simply a wave traveling through a medium. So the wave model is going to explain a couple things we're going to talk about. One is diffraction. We've already talked about that because we said that they had individual wavelengths, which we talked about wavelengths when we talked about sound. It's the distance of one cycle. So diffraction is very easily explained as a wave, but it doesn't take into account these other things. So the other two things we're going to talk about are interference and polarization. So interference, there was a scientist named Young who had what's called the two-slit experiment. And you can see here, sometimes it's the double-slit experiment. But he had a piece of paper with one slit in it, and he had the source of light. And what happened as the light hit the paper is that it would come out in bands like this, very similar to like constructive interference, because this light is not being transmitted, only the one coming through. Now once the light left that paper, it went to a second piece of paper that had two slits in it. And then what happened was he had a detector, and over time he saw that the most concentrated bands are right there in the center, and the bands became more diffuse as they went out, which means there's not as much light coming to the outer parts as the inner parts. And that's because the light that's here in the center is building up constructively. They're overlapping the troughs and crests the same way, and they are building up. And then you have periods of destructive forces where there's no light. It's all dark, for the exact same reason that when the peaks and the troughs overlap each other, they cancel each other out, leaving darkness. So what this told us was that there is constructive and destructive interference, which we knew very well from sound meant that light behaved like a wave. Now, polarization is going to be the alignment of electromagnetic fields to produce a really unique phenomenon. When we have unpolarized light, there's a mixture of randomly orientated fields, but when we have polarized light, the electric fields oscillate on in one direction and we have no light pass through. So I'm going to post, there'll be a video where you can see what it means to have the polarized and unpolarized light available for you, because it's best seen done, and that way you can understand what's going on. But for the most part, the most common example you have is if you have a pair of, you don't want to spend a lot of money, you buy a pair of cheap glasses that don't have polarized lenses, you know that they're not going to protect your eyes as well from the sun as the polarized ones. And that's because the polarized lenses are going to darken out the light a lot better than the unpolarized ones. So make sure you watch the video so that you can see visually what's going on with the light and the polarized nature. So current understanding is that there is a certain amount of energy that comes in like packets. They're like little packets of energy, like an electron. We say that it's quantized, which means it has a certain value and amount. And then each one's equal, so each electron has the same -1 charge, and a photon's going to be similar. The energy comes in discrete quanta, so individual, in unique photons. And then we're going to call them photons, particles of light, and they're very similar to electrons, except for it makes up light and not an atom. So the modern understanding is that, in fact, it's both. Particle like nature of light is that they're photons. Okay, it's what explains the three things we talked about: the mirrors, the prisms, and the lenses. Now, the wave model says that these photons travel in wave patterns. So if we think about this atom structure right here, when we have light coming in, the electron can be bounced up. So we know that, one electron is worth a certain photon of energy. But what we didn't understand was what was happening when light was behaving as a wave. Well, as it turns out, the electrons travel as a wave, which gives them distinct wavelengths, but they're still able to behave like a particle. So this is the current understanding, is that while sound is a wave, purely a wave, that light is going to be a combination of wave and particle, because light are made up of photons traveling in the form of a wave, which is similar to sound. Okay? So make sure you understand those, go through the notes again, and make sure you follow up with the YouTube video about the polarization of light.